Okay, so what is this idea of torque? It's this quantitative measure of the tendency of a force to cause a change in an object's angular velocity. It causes an angular acceleration. All right, so let's go back to this again. The amount of torque put on a bolt depends on the size and the orientation of the force and the distance from the axis of rotation. So if this was our little bolt again, our axis of rotation would be right there in the center of the bolt, and we're going to abbreviate that AOR. So when you see that, AOR means axis of rotation. We use a symbol tau, and it just sort of looks like a fancy T. You kind of go like that. That's tau. And the units are Newton meters. And if we apply a force here, you might get it to turn a little bit. If you apply a force here, you'd get it to turn a little bit more. This is where you would get your maximum torque, and you'll see why shortly. This again, torque equals 0, and it's because it's actually pointed along that imaginary line where the axis of rotation is. So let's get into torque. We have a couple things that we want to know. We have a vector from the axis of rotation that we draw right from that directly to where the force is applied. That is called your lever arm. So R is your lever arm, so that's the distance. F perpendicular, we're going to look at F perpendicular. That's going to be the perpendicular component of the applied force. So if this is my original applied force, this blue vector right here, that's F. We can just break it into vectors like we normally do. We have F parallel, and then we have F perpendicular. The only part of that force that's going to give torque is this perpendicular part. So that's the only part. And if you multiply this distance times the perpendicular component of the force, you're going to get the amount of torque. Now, the direction of torque we're going to look at a little bit later in detail, so don't worry too much about it. But you can imagine that if you put a force on this wrench like this, that it's going to rotate up this way. So you can intuitively imply that it's going to be counterclockwise. Okay? All right, so let's look at this. It's the same picture. Here's my force, force perpendicular, force applied. Let's look at it a new way. Like if we put these two vectors tail to tail like so, because remember you can pick up a vector and you can move it anywhere in space. You just can't move it around this way, but you can pick it up and put it anywhere you want. And then here we go. We could have our lever arm or lever arm, tomato, tomato. And then there's your force. If we were to break it up now, you can see that your force perpendicular is just F sine theta, right? That's where this comes in. So we could write torque as R times F perpendicular, or we can do this. Whoops. It's called R cross F. It's called the cross product, and it's just some vector math. But what happens is if you do R cross F, it gives you back a vector. So sometimes they call it the vector product. And I have this little note down here. Remember doing work, and we learned the dot product? That gave us back a scalar. And if you remember, the dot product used the cosine, because when we did work, we did F dot R, and that showed us how parallel the one was to the other. Well, the cross product shows us how perpendicular these two vectors are. We just want the perpendicular part of one of them compared to the other, because again, this is the only part of that force that's going to give any torque. All right, so a couple little, there are little messy notes, but a couple notes about the cross product. So we can write that vector A crossed with vector B is going to give us some new vector. Now the magnitude of this new vector, this magnitude of vector A perpendicular to B times the magnitude of B. So again, this is going to be like, if we say it, A perpendicular to B times the magnitude of B is going to give us the magnitude of vector C. Well, if you remember back with the dot product, that was commutative. And if we did A dot B, that was equal to B dot A. It's not the case in the cross product. In the cross product, if you do A cross B, then that's going to be the same exact magnitude as B cross A, but it'll be the opposite direction. And I'm going to gotta give you a hint to it. It has to do with the right-hand rule that we talked a little bit about, and we'll talk more about it after we get some basic torque under our belt. So just remember that the magnitudes don't matter. If you do A cross B or B cross A, the magnitude is going to be the same. It's just you can get your direction later. So it's pretty powerful to realize that, and I'll show you some examples. So this is what this is saying, the magnitude. It doesn't matter if you take the perpendicular part of R or if you take the perpendicular part of F. Those magnitudes are going to be the same. And you can always do the direction independent of finding the magnitude. All right, so let's look. Let's do a simple torque problem. Here's our wrench. Here's our bolt. This is our lever arm, because I take this vector and I go from the axis of rotation. I go all the way to where that force is applied. And that's my R. I'm going to tell you that length is 10 centimeters or 0.1 meters. Well, if I apply a force right here of 5 newtons, then I know that my perpendicular is going to be 4, and then my parallel is going to be 3. So a 3, 4, 5 triangle, right? So you then just say, okay, well, you know what? Torque is R cross F. R is 0.1 meters. And then the perpendicular part of my force is 4 newtons. And then I just multiply them together. Okay, so we have 0.4 Newton meters for our torque. Which direction is it going to rotate? It's going to rotate this way in a clockwise direction. So intuitively, you can say, oh, well, clockwise, that's going to be negative, because we kind of talked about that before, that we're going to say anything rotating this way. Anything rotating clockwise is going to be considered negative. Anything rotating counterclockwise, but that's not always the case. You really have to see the right-hand rule when we actually are together. All right, so let's do another one. What if you have something, this is going to drive home that idea of it doesn't matter which perpendicular you take. What happens if you have this box, and it's 2 meters by 2 meters, and then we apply a force to this corner? Well, we can kind of anticipate that it's going to want to rotate this way, right? But it's kind of weird. If you were trying to find the perpendicular part of the force compared to R, this is R, Doesn't look like an R, it looks like a V, but that's an R. So what you can do, really useful trick, is you can look and you can draw something called a line of action. It's an imaginary line that just acts in the direction of the force. So if you draw a line of action through your force, you can extend it in both ways, then you're all set. You can then, let me get that out of the way. You can then go back, let me shorten him up a bit. There we go. You can then drop your perpendicular from your axis of rotation straight down here. This is called your effective lever arm. And that's going to be when you use your line of action. You see it? Here it is. Okay, so let's figure this out. Let's figure out the net torque on this box now. We know, start with your equation for torque. You're going to say torque is equal to R perpendicular F this time. The force is 10 newtons, so I know that that's 10 newtons. And then what's my R perpendicular? What's this right here? Just 1 meter, right? Because if this whole side is 2 meters, then the length of that is just 1 meter. And my net torque will just be 10 Newton meters. So it's really, really helpful to be able to draw that line of action when you have a force that might be kind of oriented in a way that makes it kind of complex. Okay? All right, so let's say we applied a force. Let's say that force was really here. What's your net torque? But I can't see the chat. Someone unmute.
Is it not the same?
It's not the same. And why would it not be the same?
Oh, wait, it's not going down. Oh.
Yeah, so pretend he's not even here. And here. So let's say I just have the box. Now you might be able to see it. If I...
But then...
Yeah, go ahead.
So, the force is still 10 newtons.
The force is still 10 newtons. What's my R perpendicular to the force? In other words, here's my R, because it always starts at the axis of rotation and it goes to where the point of application of the force is. How much of those two vectors are perpendicular?
Zero.
Zero. So the big idea there is if your force, if your line of action of your force goes through your axis of rotation, it doesn't apply any torque to it at all. If I push on that box right there, I'm not going to get it to rotate at all. I might get it to slide if it's not fixed to something else, but I'm not going to get it to rotate at all. So my net torque on that would be 0. All right, so we'll play around with some more of them. Let me put this back. real quick. We'll get rid of that. Okay. All right, so big idea for this one, line of action, always a good idea. You can do R perpendicular, so you could go from the axis of rotation to that line of action, or you could break up your force and figure out the part of the force that's perpendicular to R. Doesn't matter for the magnitude. For the direction, yes. All right, so let's do another one. Here we have a meter stick. The centimeters are on the bottom. We're going to say the meter stick has a mass of 0.5 kilograms. I have the axis of rotation over there on the left. Let's figure out the net torque. I have a little green dot there. What do you think that little green dot is for? What does that show you?
Is it the axis of rotation?
I'm going to have the axis of rotation over on the left, the pink dot.
Oh, okay.
So the green dot's going to be what?
Would that be the center of mass?
You got it. So that's going to be the center of mass. So the next few slides are going to be about this little meter stick here. Let's figure out the net torque. We know that if we let go, it's going to go down this way, right? So here's our process. Identify all the forces acting on it. The only force would be the weight. So it would be the gravitational force, which is just mg. Where's my lever arm? So you want to identify your forces, and then you want to identify your lever arm, and that lever arm is always going to go from your axis of rotation to the point of application of the force. So that's R, and then this would be F, specifically FG. Now we need to figure out, okay, well, I want the perpendicular part of the force. Well, this one's a nice easy one, right? The torque is going to be R cross F. Or you could say RF sine theta, right? What's the sine of 90 degrees? So the sine of 90 is 1, so that just means that that whole force, since it's perpendicular to that R, that whole force is going to cause a torque. You get your maximum torques that way when they're perpendicular to each other. So at this point, all we have to do is just multiply the 0.5 times and my R is 0.5 meters because it's a whole meter stick, so halfway is 50 centimeters or 0.5 meters. So it's 0.5 times the whole entire force, which the mass is 0.5, and let's use 10 just to make life easier. So your net torque is going to be 2.5 Newton meters. Make sense?
Why did we do 0.5 two times again?
Okay, so this is R because it's halfway. That's where your center of mass acts on a meter stick. So that's half a meter, and then this is the mass up here.
Oh,
And then
right.
yeah, and then this is G. All right, cool. So what happens? It starts to rotate downward. Let's look and see what do we do when it gets to look like this. Now it's 30 degrees below where it started. And we're going to do this both ways. Remember that the whole meter stick has a constant angular velocity. It'll all be moving, like that whole stick together will move. But we know that different points on there are going to have different tangential velocities, so I just remind you of that. Let's identify the force that still acts straight downward. Fg is what, 5 newtons, because it still has the same mass. Your R goes like so. That's your R. That's still 0.5 meters. But now we got to make a decision. You can do it one of two ways. You can break up your force. Wow, that's too big. You can break up your force, right? And what would this angle be if you broke up that force? Got to do some geometry. Maybe, I think if we do it the other way first, it might be easier to figure out what that angle will be. It doesn't look... Let's do it the other way first. I'll get rid of these because they were too big anyway. All right, let's draw a line of action. What's a line of action? What would that look like? A vertical line or a horizontal line?
Vertical.
Yep. So we're going to go and draw this imaginary line of action like so. Cool. So now what we need to do is just break up our R vector into X and Y. And I think if I move this down and showed you that this was 30 down here, it might be a little bit easier to see. Let's move 30.
So 0.5 times sine 30.
You got it. So R perpendicular is going to be 0.5 times the sine of 30 degrees. Awesome. So now what? We've got it all. We've got everything we need. We can go, the net torque is going to be R perpendicular F, which is going to be 0.5 sine 30, and then the force is still 5 newtons.
So you don't need to put any like angle.
Oh, this isn't sine. Hold on. This is cosine. I messed up. You messed up. We all messed up. We all messed up. That's all right. I just went right with you. And you'll see why. Well, you won't see why, but that's okay. It's 0.5 cosine 30 because this is our adjacent side.
Oh yeah, I was looking at the wrong one.
It's okay. You're going to see, Jill, we're going to use sine in just a second. So it's all good. That's why I so readily took it. So it's 0.5 cosine 30 times 5. What is my net torque? I don't have my calculator right here.
Oh, so you just multiply that, so
Yep, just
how
multiply
come?
that.
Oh yeah, because the last one we did sine 90. But yeah, it's not.
Yep, so this is just different. So your diagrams and figuring out which is perpendicular, because that's what you're really trying to do. You're trying to get the two vectors that might not be perpendicular. If they're not, you need to figure out the components that are perpendicular. So you have to break up one or the other. And visually, it doesn't matter to get the magnitude of it. And then we know that this is rotating this way. So we could say it's going clockwise. But we're just looking at
So
magnitudes right now. So what's that number?
2.17.
2.17 Newton meters. Awesome. So that's one way you could do it. That's if we took our perpendicular. What if we went and did the force and figured out the perpendicular part of the force? That's where we started, and we started to go like this. We said, okay, well, let's break this up. And what we were interested in was trying to find this angle. So let's do a little bit of geometry. If I make this imaginary line here, this is 30, and it's a little bit easier to see now. Then this is 30. So that makes this 60. This this is my blah 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 F perpendicular. So I could, let's just make sure that this works out, that my net torque, I could take my net torque and do my R times F perpendicular. Well, my F perpendicular is going to be F cosine 60. Hold on a sec. I'm going to pause. Hold on. Are those vectors, do they have any perpendicularness to them?
No.
No. So my net torque is going to be equal to 0. Okay. All right, let's try this. When we have strings that are wrapped around a pulley or a chain or a gear, this is what we like to see. It's easy. And the reason that it's easy is because the string always pulls perpendicular to the axis of rotation. Take a second, draw your lever arm. start at the axis, go out to the force. That's my R. And it's just the radius of the circle. So you can easily figure out your torque because you're going to do R cross F. They're completely perpendicular to each other, so you just multiply the two together. So we love pulleys, we love strings. So my net torque is 1 Newton meter. Anybody know what the English units are? You've probably heard of them. You might just not know. The English units are foot-pound. This many foot-pounds of torque. So if you were to go into like Pep Boys to go get a wrench to fix your car, it would be rated in foot-pounds. Okay, so let's also make another little quick note too, that the further out you are from the axis of rotation, the more torque you get because it's part of your equation. So you could have a small force but a really long wrench, or you could have a really short wrench and a huge force, and you could end up with the same torque. So the length of your lever arm, really important. All right, go ahead, try this one. Keep in mind, this guy wants to rotate it this way. This guy wants to rotate it this way. Their lever arms, though, this guy, you could say that's R. And then this lever arm, look, they're both completely perpendicular. So now we finally have more than one torque. We're going to actually write out the net torque. Will this be a positive or a negative? This one's going clockwise. So conventionally we say negative. This is going counterclockwise. And we're just saying positive. It's sort of like the battle of the torques. This guy wants to pull it this way, this guy wants to pull it this way, but this is a bigger force with the same lever arm, so this guy's going to win out, so it's going to rotate clockwise. All right, what's this guy? If you did physics last year, you probably had problems like this. What this is like two wheels fused together, but they rotate as one object. So like from the side view, it would look like this. It's just that this has a smaller radius. So we say that this has a radius of R, this has a radius of 2 R's. Now we have 3 different forces. They're all the same magnitude. So you're not going to get an actual number, but let's get what's going on. So here's how I approach it. I would first be like, okay, you know what? That guy's going to want to make him go clockwise. So I'm going to put a little negative. This is going to want to make it rotate clockwise. This one, though, wants to make it go counterclockwise. Now, it doesn't really matter as long as you're consistent. If you were watching a tutorial and they counted them the other direction, as long as these both were positive and this was negative, it's okay. You just have to stay consistent. So I'm going consistent with our book. All right, so you already have your lever arms. You have the idea of what they are. This lever arm is shorter. This is only R. This lever arm is 2R. This lever arm is 2R. Now just add up all your torques. So I just going to go around the circle. Negative 2R times one of those. And then this is the same exact force, so negative 2RF. And then this little guy is positive. And he's only got a lever arm of R, but it's still a force, same force. So that's negative 4 plus 1. So we end up with a net torque of negative 3R times F. So it's going to rotate which way? Counterclockwise or clockwise?
Counter.
Counterclockwise is positive.
Oh, clockwise.
There we go. Awesome. So here's this idea of static equilibrium. You'll see, like if you want to build a bridge, you certainly don't want any linear acceleration and you certainly don't want any angular acceleration. So what you have to do is make sure that they meet these conditions, that your linear acceleration has to equal 0 and your angular acceleration has to equal 0. And the way to do that is to make sure that all of your net forces are going to equal 0 and all of your net torques are going to equal 0. Those are the conditions. Let's see what we got to do. So here's some examples that would not qualify. Let's say I apply a force of 5 newtons. Here's my center of mass. We'll have the same center of mass for each of them. Well, your net force is not going to equal 0, right? Your net force does not equal 0 because we know that there's an acceleration that's going to be 5 over m. Let's just say that these guys are 1 kilogram. So my acceleration in the x direction would be 5 meters per second squared. And then we know that we would also have a net torque. Your net torque would also not equal 0. It is not in static equilibrium. This thing's going to rotate. All right, what happens if we apply a net force of 5 newtons this way, and then we have a net force of 5 newtons this way? Does your net force equal 0? Yes, awesome. However, does your net torque equal 0? What do you think? There's your hint. Imagine if you have this object here, right? And you're pushing at it this way, and then this is pushing this way, that's going to get it to spin, isn't it? So it's going to get it to spin. So your net force does not your net torque does not equal 0. You will have an alpha. So even though your acceleration equals 0, your alpha, your angular acceleration, does not equal 0 in this case. All right, so what happens if I have a net force this way? Oops. I mean, I have a force of 5 newtons this way, and then I have a force down here of 5 newtons. And again, it's a 1 kilogram. Is it going to rotate? What do you think?
No.
It's not going to rotate, right? These two torques are going to cancel each other out. This is going to want to try and get it to rotate this way, and this one's going to try and get it to rotate this way. And since it's going to be rotating around its center of mass, those two are going to cancel each other out, because this guy's going to be negative, this will be positive. So your net torque is 0. Does equal 0. And your alpha equals 0. But what is your acceleration? So if you add up all your forces, sum of all your forces is going to be 10 newtons, and it's going to be 1 kilogram again, A. So your acceleration is going to be 10 meters per second squared. So you got to be careful when you're doing equilibrium problems, because there are a whole bunch of different scenarios that look at first like it's in static equilibrium, but it's not. So this is sort of like if you remember doing static equilibrium without rotating objects, where we had tensions and all the tensions had to balance out in all the directions. This is that plus this extra step of making sure that you have no net torque either. So here's an example that does qualify. If we have 5 newtons this way.
Wait, on the previous slide,
Yes.
was it not equal to 0 or equal to 0?
None of these qualify. Our net torque is 0.
Because
Hold on. What happened to my draw? My draw went away. I hope it comes back. My net torque equals 0, but my acceleration does not. So it's still going to accelerate to the right, but it's just going to be like one.
so why is there a cross in all the equal signs?
What?
Wait, why is there like equal signs with like crosses in them?
Oh, because in this second, you mean the second example?
Yeah.
The net torque does not. This will rotate, so your net torque does not equal 0. Oh, the alpha does not equal 0.
So it only equals 0 in the third one.
The net torque only equals
the
0. Yes. But none of them qualify for equilibrium, because in this case we have a linear acceleration. In this case we have an angular acceleration, and in the third case we have a linear acceleration. Okay, better?
Yeah.
You sure? Okay, because I might have, I might have added something I shouldn't have. Is my drawing back? Oh, good. Phew. Okay, so here's an example. We get a 5 Newton force here, a 5 Newton force here, and then a 10 Newton force here. So if you look at this, you can kind of see at this point that yes, the forces to the right are going to balance out your forces to your left. So our net force equals 0. Now, if you look at this, this is going to be clockwise, this is going to cause a counterclockwise, those are going to be equal, and this guy goes right through our axis of rotation, so it doesn't have any torque on it. So the torques are also balanced. So my net torque is also equal to 0. So in that case, that object is not going to accelerate linearly or rotationally. So that's a visual of what it would look like. So you want to try one? I think we have, oh no, we're running out of time. Okay, real quick, we'll do this. These are just the steps to go through and solve equilibrium problems. What I will do is later, like during 9th period, I will run through the examples that I have left on the slide, and then I will upload it to Schoology so you can go through those examples. And if you get stuck on anything, you know, just reach out. There's my alarm so I don't run over. Okay, so I'm gonna pause.